All right. We'll call this modeling population growth, I guess. Modeling population growth or changes in the population. And of course, we're going to try to use a little bit of a mathematical thing. But the mathematics of this is really very straightforward. What I notice is biologists are not really mathematical, but they like to pretend they are. So they often take a simple thing and try to make it more complicated than it needs to be mathematically. And I think that's the case of what's happened in your textbook. So let's clear up some of that right off the bat. Okay, so population changes or population growth. Essentially, that's what we're looking at here. The first thing that they talk about in your textbook is exponential growth. Now, there's different kinds of growth because there are different conditions that populations live in. All right? Exponential growth is basically a continuous, steady growth rate that on a graph looks something like this. It just keeps going up. We don't often see this in the natural world in most circumstances because most circumstances are limited. You'll recall from grade 9, right? They're limited by a value called the carrying capacity, which sort of means that once a population gets to that point, the resources that it's depending on become depleted. And so instead of this growth that keeps on going, what we usually see is growth that could be exponential at first, but then tends to wobble up and down around the carrying capacity. And that's because, of course, if you get too far above that dotted blue line, that means you're running out of resources. There's increased competition. There's increased disease. There's all kinds of things that come into play that cause the population to sort of dive back down a bit. And if you go down a little bit too far below that line, then you suddenly have extra resources available and the population comes back up, right? Remember from grade 9 ecology. And so that's typically what happens. This part of the graph is not exponential growth. In fact, it's not really growth at all. It's kind of an equilibrium, almost, well, we could call it a homeostasis, right? Because it is, in a sense, a homeostasis where you've got, this would be, imagine blood sugar levels. The graph would look the same, wouldn't it? As your blood sugar rises, it hits that homeostatic level and it wiggles. Okay, so this part of it, we're talking about exponential growth. We're talking about sort of this section of the curve. So this would occur in a population where there's perhaps, maybe there's been a massive die out. Some environment, a forest fire wipes everything out and resets the clock, so to speak. And now there's all this massive growth in the area that's not at the carrying capacity, right? Or something like that. Okay, so in terms of talking about exponential growth, your textbook gives you a bunch of sort of letters and numbers that they use. So the first thing they talk about is the birth and death rate. Obviously, if we look at the factors that affect growth, the birth rate and the death rate are pretty much very important numbers, aren't they? And so the overall birth rate is called B, capital B, and the death rate is called D for obvious reasons. Now there are other factors that do affect populations, and that would be, in particular, immigration, which is when animals move into a certain area, and emigration, animals moving out of a certain area. Now, these two things are a little tougher to figure out, right? They're a little harder to work with. Typically, in many populations, they almost cancel each other out. Because of this sort of even equilibrium that is established, what you often will see is that if you have a population of foxes in a forest, some might move into the area, but then some might also move out of the area. So there tends to be kind of a canceling effect that can happen with this, and it complicates the issue. So for now, I think your textbook is focusing just on these two factors. It's not worrying about those, kind of considering them to be a bit of a wash to keep the computation a little bit simpler and just for learning the concepts, right? Okay, Now, how many of you have taken calculus? None. So in calculus, calculus is the mathematics of changing things. That's what it really is. It's how we describe changes in math. And so a population change right? A population change, or what we might call the rate of change, how fast it's changing, or rate of change, is described in calculus like this. A little d and an n, and a little d and a t. We say dn by dt. And the little d comes from, you remember this symbol? Delta in math, which means changing. Well, the little d is a symbol that just means changing by tiny, tiny, tiny increments. So it's just a version of this that means that the changes are very, very small. And it's not important for us to understand all the calculus of it. We just need to know that this symbol represents the rate of change in a population size. That's all we need to know. Now, they're going to use little d's later in the book for per capita death rates. Do not confuse those little d's with these. Think of this as this, not anything that has d's in it. That's just a mathematical symbol, okay? So that's going to be the growth rate symbol. And it has nothing to do with any of the other d's that occur later. Okay, and they make the statement, simple statement, that if you have birth rates which are adding to the population and death rates which are taking away from the population, then you can calculate sort of a rough estimate of the growth of the population or the rate of change of the population by taking the births that you get minus the deaths. That makes sense, right? If you have 10 births and 5 deaths, you've increased by 5. It's not difficult. It's very simple. Okay. Now, what we do is we define some other things. This big capital B would be the number that are being born in the entire population. As we said before, we don't measure stuff like that because it's too hard to go and count everything. So we tend to rely on the estimates that we've produced by sampling. And so typically, instead of the big capital B, we call the per capita birth rate, which is the birth rate divided by out of the total number of people, or a total number of individuals. So this would be, if there's 50,000 foxes, out of those 50,000, how many births are there? Maybe there's 200 or 2,500 or whatever. So it's just taking that birth rate and comparing it to the overall population size. And your textbook gives that the symbol little b. So it's like a smaller sort of sample, right? It's per fox. And of course, that birth or death rate can be a decimal. It can be 0.5 or 1.7. That doesn't mean that a fox is giving birth to, 2 legs, a stomach, and a head, and part of a fox, right? It just means that on average, you get these decimals. Like, for instance, the human per capita birth rate, I think, in Canada is probably somewhere around 0.95 or something, or 1.27. Obviously, that doesn't mean you get half of a little sister. It means that on average, it works out that way. And then they talk about the per capita death rate, which again is comparing the actual rate of deaths to the population size. So it's D over big N, and they call that little d. So now that you understand that, it might make more sense as we go on to figure out what all these things are for. Okay. Now, here's where they go crazy with their mathematical stuff in the book. All right? What they do is they use the equation on this side, and they use the equations over here on the right, and they combine them. They mishmash them together. So, from your math, you know that we can take these two equations over here and rewrite them. Maybe I can just do it right here. I'll do it in a different color so it stands out. This equation can be isolated for capital B, right? If I multiply n to the other side of the equation, I get capital B equals little b times big N. Does that make sense? Right. And the same over here. I can write that capital D is the same as little d times big N by multiplying both sides by n. And then, if I take these little things, I can substitute them over here, because I can replace now the big B with the little b and the n. Because remember, the big B is probably something I wouldn't know, or it's something I want to figure out, because it's too big to go and count all the baby foxes. But I might know, because of sampling and estimates, what the little b is. So it's better to get the big B out of the equation by replacing it with an expression involving the little b, which is more of a known number. Okay, so that was a good question. This little d right here has nothing to do with the d we see over there. That's a mathematical symbol that happens to have the same letter. You could consider, maybe, if it's easier for you, you might want to just consider this a big capital R to stand for growth rate, or a big capital G, and then it would eliminate that problem. I think what this textbook is trying to do is it's trying to show you the calculus part. And believe it or not, if you go into population dynamics, there is actually calculus involved. Calculus is a weird math because it shows up everywhere. It shows up in business. It shows up in projecting stock prices, and it shows up in marketing and how you can maximize and minimize profits. It shows up in biology as growth rates. It shows up all over the place because it's the mathematics of changing things. So believe it or not, you may have to learn a little bit of calculus if you do go into a biology program at some point. Kind of interesting. Anyway, let's go back to that. So where were we? Small. The big B turns into the little dn because of this equation. They are the same thing. And the same thing happens with the big D. Big D is the equivalent of little d times n. So we've substituted those two things into the equation. And then we get this growth rate, R, call it what you want, as B minus D factored out from the n. If you multiply this n back into these brackets, you'll be right back where we started up here. So this is just a shortcut, this bottom step, okay? But instead of this R, I'm just going to erase the R. Instead of this R, we use the mathematical symbol dn by dt, which has nothing to do with the other d. And that's how they arrive at this little expression that you see on the bottom of page 601. So all of this here is just fooling around with the numbers, and none of these things are overly critical. Here's what you should know out of this. You should know how to calculate a per capita birth rate by dividing the birth rate by the total number, and how to do a per capita death rate. And then you should know this is how you calculate the change. That's the three things that are critically important from there. Okay? All right. Now, to make it even more confusing, this is why I didn't want to use a big capital R here for these things, because they use a little small r for something completely different. All right? What they decided is they don't like the look of this equation right here. It looks too complicated for biologists. So they like to say, let's just call the difference, the B minus D part, let's give that a little letter and call it baby r. That's all they're going to do, which means that this now becomes dn by dt r times n. And now it looks like an easy formula. The problem is you just have to memorize extra letters. So personally, I've always just used this formula because it makes perfect sense. This part could be called r. We could also call it unicorn if we wanted to, and I think that just kind of complicates the issue. But your textbook we'll use this. And you have to remember that when they do that, R stands for the difference in the births and deaths. And it's the per capita births and deaths. Notice that. It's not a capital or D or B. It's the difference in the per capita birth and death rates. That's what the little r stands for. And so if you see that, you can see that that's how they get to where they're going. Now they also do another thing. They also say, okay, so that's true for populations of wildebeest that are growing and being born and dying. But they like to imagine what would happen if the wildebeest lived in the most perfect utopian world where there was no other problems, no predation, no disease, a lovely, wildebeest heaven. That would allow for the biggest possible sort of, if you think about what would happen to this in wildebeest heaven, is births would be skyrocketing and the deaths would be dropping, because why would you die, right? There's nobody hunting. It's an idealistic situation. And that means that R, because if the B is getting bigger and you're subtracting an ever smaller number, the R is going to shoot up and be large as well. The difference in those would get bigger. So in ideal conditions, which don't really exist, but we can have this equation. And what they say is that would result in the biggest possible R you could get. And so what they call it is R max, R with a little subscript max. And then times, whoops, I don't need the brackets, times the big N. So this is just another way of describing the most ideal kind of growth that you could get. And what that does is it establishes sort of an upper limit, right? If this is the best possible scenario, then we can factor in the other things like predation and so on, and we can sort of say, okay, we know that's never going to be the number, but it gives us a ceiling, right? It gives us sort of a maximum that we can use as an upper limit. And that's what that stands for. So you'll see that in your textbook as well. Okay, the next thing. Any questions so far? All right, I'm going to change colors again because we're talking about a whole different thing now. Another thing that biologists like to keep track of is what's called a doubling time. A doubling time. In other words, how long does it take for the population to double? How long does it take for the population to double in size? Why not triple? Why not 1.7 times size? I don't know, it's just kind of an interesting thing, the doubling time, right? It's kind of a convenient way to describe growth. And so what they do is they take a rather complex logarithmic formula and they whittle it down for you. So in other words, they've done some stuff, some mathematical stuff, and they've worked it all out to add up to a certain number. TD. Again, this D is not death. This D stands for double. So again, it's a little bit confusing. But it's just a subscript. It's just an identifier. It's not a number that's going to be involved. TD is simply equal to the number 0.69 divided by the little r. So the top of this is sort of already figured out for you so that you don't have to worry about the complicated math. And it comes out to this number. So we sort of whittled it down to this in the textbook as the doubling time equation. Okay? Now, the little r in this case, it's expressed as a percent. Expressed as a percent. So the doubling time, so let's say you had a population, if the growth rate which we call R, is 4%, then we can calculate the doubling time by putting in T. Hang on, I'm going to erase this, and I'm going to pause for a minute and recalibrate because okay. Then the time to double is going to simply be 0.69. So the top never changes. It's worked out for you. Treat it like a constant number. And then you're going to divide that by 0.04. And then the answer would come out to about 17.25 years. So it would take about 17.25 years for this population to double. That's, of course, assuming that the conditions don't change and that it's in a utopian ideal situation. As I said before, typically we don't have this kind of growth, and it's only temporary until we reach that carrying capacity, okay? So there's the next thing that's in your textbook. Okay, then we have limits to this, of course, the limitations. Well, it only works, so this logarithmic growth, or exponential growth as they call it, I'm just going to put this type of growth, is not very common. It only happens or occurs under strict conditions. So like I said, it might happen temporarily while after a forest fire, when it's sort of like fair game and there's all kinds of resources to be exploited and populations grow. After an intense famine that wipes things out, or a plague or a virus like coronavirus, right? Oh, scared. If it had been instead an Ebola virus, by now a very large portion of the population might be wiped out, in which case there would be lots of resources available for the people left over, okay? It's actually quite good for very specific things. So it works best, I'm going to say, for populations that grow continuously. Grow continuously. Typically, that's not true for many things. They sort of grow in spurts, right? They have longer breeding seasons, and so their growth sort of goes in spurts and then stops and shorts and stops and spurts and stops. But continuous growth is something like this. For example, bacteria. Bacteria grow pretty much continuously. They're always in a state of constantly dividing, right, at any given time. At any given time, if you have a petri dish full of bacteria, a whole bunch of them will be splitting. And then if you wait 5 minutes later, different ones will be splitting. So there's always splitting going on. There's always growth or reproduction happening. Whereas if you think about a herd of caribou, well, there's only growth at certain times of the year. They have a mating season, they meet, they do the rut, 6, 7 months, 9 months later, babies are born, and then there's your sudden growth, and then it's another year, so it's not quite continuous. Because during all that time, things are dying, there's predation, there are things that are changing. So this is more of a continuous growth pattern that we've discovered so far. And it can happen in wildebeest if there's a giant forest fire and now, you know, there's lots of resources. But typically, bacteria are probably the best example for this. Okay, so now we get to the next thing, which is what we call the logistic model. Instead of the exponential model, the logistic model takes into account a few of these other things for populations like humans, wildebeest, frogs, foxes, and things that aren't going to continuously grow. And basically, what this means is that these particular things tend to grow to a point. The carrying capacity oops, carrying, not carry capacity, the carrying capacity. Let me just rewrite that. Carrying capacity. It's the capacity or the number of individuals that the environment can carry, that it can support, right? And that's from, you learned that in grade 9. You might not have called it the carrying capacity in grade 9, because I noticed in some of the books they changed the name because I guess this was too hard to spell in grade 9 or something. And then you have to relearn what it's really called. They sometimes do that in grade 9 and 10. They simplify too much, and then it's like you're learning a whole new thing, and it confuses people. So what this essentially means is that a population, rather than growing like this and just growing on, as the population gets high, above this line, as I said, resources become scarce, more disease causes the population to drop. And then as it goes below the line, then there's more resources available because there's less people sharing it, or less boxes or whatever, and the population can go up, and we get this warbling effect. So most population graphs look something like this, where the population is just sort of wiggling up and down along that carrying capacity line. Unless, of course, there is some environmental thing, an event that causes that to drop. So, for instance, if there was a severe drought, well, severe environmental changes mean that the environment can no longer support that. It changes the carrying capacity of the environment, and we would see this fall. If the event was something that repaired itself over time, like a forest fire, what we would find is for a while the forest fire had happened, the population would drop, and it would sort of develop a new carrying capacity in the new burned out environment. But as that environment repaired itself, this would grow back up again and remain at the original carrying capacity. So it all depends on the environment. But in a non-changing environment, carrying capacity should remain relatively similar, right? Unless there's a big event that happens. You can imagine big events like an ice age would change the carrying capacity for thousands of years, whereas a forest fire might change it for a year or two. A drought might change it for a few months, right? It all depends. So now this logistic model is going to sort of take all this into account and give us some idea. All right. So what we need to do is we need to adjust our little formula from before to account for this carrying capacity. So the carrying capacity is represented by a capital K. Okay? That's carrying capacity. I guess C has been used for too many other things, so you use a K to keep it from getting confusing. All right. So now, what we do is we take the growth rate, which is d, n by dt, right? And we said it was R max times n. But we need to sort of adjust this. So what we're going to do is we're going to multiply this by an adjustment factor. And so the adjustment factor is this, k minus n over k. So that's the adjusted sort of formula, right? Now let's talk about this factor and what it means. Well, if you have a very small population, then that would mean, let's say you had 2 foxes in this entire whole region. Those 2 foxes would be having a heyday. They would never run out of food. There'd be resources galore. And we would expect that they would start to grow exponentially, continuously. There's not much stopping them. Look what happens to this. If the number is small, if this little n right here is a very tiny number, then that is essentially just k over k. K minus almost nothing is pretty much still k, right? And so that turns into a 1, which makes this factor a 1, which doesn't affect anything, and brings us back to our original exponential growth equation for small populations. As the population gets bigger, though, what happens is this turns into a sort of a percent. Let's imagine an n that's about half the size of carrying capacity. Well, then this doesn't become 1, it becomes more like 0.5. So as n becomes larger, the value of this k minus n over k gets smaller. So it might be 0.5 or 0.7 or 0.6, which effectively means when you multiply by a fraction, this gets cut a little bit, doesn't it? It gets reduced by this factor. So this is a reducing factor based on the numbers in the population and the carrying capacity that help us understand the closer you get to the carrying capacity, the less exponential and continuous your growth will be, and the more uppy-downy around that carrying capacity it will become. What would happen? The question was, can n be a negative number? N itself can't be negative, but the value of k minus n over k, if the number of individuals grows so that it is bigger than the carrying capacity, then the top of that fraction would be a negative number, wouldn't it? Maybe it's 12 take away 14. And then you would get a negative percent for the value of this entire thing. That would represent a decline instead of growth. It would mean that the growth rate, if you get a negative growth rate, that would mean that the population is dropping, not growing. So that's a good point to make. All right? Now, what you'll notice is, if the number reaches the carrying capacity, what happens when k and n are pretty much the same? Well, let's look at that again. Let's say you grow, you grow, you grow. Well, if k and n are pretty much the same, then that's going to mean the top of that is going to be close to 0, because the same thing, if you subtract it, right? 5 minus 5, if they're very close to the same. When this becomes a 0, that means the whole thing becomes a 0. 0 over, doesn't matter what the bottom is, which means that the entire growth rate thing, if this is all a big 0, then that means this whole thing is a big 0, and that would indicate no overall growth. But typically what happens is a homeostasis. Instead of just reaching a point where you have no growth, instead, that's unrealistic, right? So what happens instead is you wobble up and down. Like I said, you don't go, if this is your carrying capacity, the graph doesn't do this with no growth, because that's just impossible in normal situations. It tends to go like this instead, and it wobbles up and down. And the wobbles can be variable depending on the conditions. And so this adjustment factor allows us to calculate the growth in terms of this carrying capacity, whereas before, all we had was this part of the line, exponential growth, and it didn't help. Okay? Yeah, I can go up. How long? That far? Okay. Your book talks about this little curve, the sigmoid curve, which basically means it looks like a sine wave. That's what I've drawn here, this little uppy-downy wiggling curve. Okay. There we go. I think that's pretty much everything there is to say. This particular thing I'm just noticing in your book, they do specify that this doesn't take into account immigration or emigration. And the reason we know that is because there are no letters in the formula to represent those things. So both of these have no sort of immigration or emigration. And I think that that's where they talk about open and closed. So an open population is one where you have births, deaths, immigration, and emigration. But you can imagine, for various reasons, there may not be a lot of immigration or emigration. If you're in a pond, then it's pretty hard for fish from another pond to get to your pond, right? So in many situations, you have what's called a closed population, where people aren't really allowed in or out. It's kind of like right now, Canada-US border is closed due to COVID. And so there's very little movement from one to the other. In that case, in the closed population, it's only the birth and death rates that have the effects on the growth. Yeah. So some of you have Googled and you found a formula that looks like this. Births plus immigration minus deaths. Now, be careful how this would be. Were there brackets on that? Yeah, there has to be brackets here. Deaths plus emigration. Because emigration and deaths are both negative things that cause things to drop. And of course, this minus sign makes this a negative number and it makes that a negative number, right? Without the brackets, it would be minus D minus E. This, and then by dividing that by the total number, right? Remember how we did B minus D over N right off the bat to get the per capita growth rate? Well, this would be an adjusted per capita growth rate that also takes into account immigration and emigration. So that's possible to do that. However, I think for everything we're doing, we're just trying to get the basic idea. So I think that most of the questions that you'll face will not involve immigration or emigration. If they do, then you can simply treat immigrations, basically it's just like births. And emigrations are essentially just like deaths, right? People leaving or foxes leaving is the same as foxes dying. So they're both negative things that detract. But they're harder to control and it's harder to count that. So it makes for a more complicated situation. So that is basically everything there is to know about population growth, logistic growth, and exponential growth. One that's continuous and one that's just with the carrying capacity worked in. So we'll stop here and then we'll go on to factors that affect growth rates in our next video. It's easier